Good morning, everyone. Welcome to the C&E Sales monthly webinar series. I'm Jeff Butler, the Technical Manager of C&E Sales. Today's webinar is Banner Engineering's SC and XS Safety Controller Tricks and Traps. Our presenter today is Heinz Knackstedt, C&E Sales Safety Specialist. If you have questions, please submit them using the tool on the right side of your screen, and we'll address them at the end of the webinar. I'll now turn the webinar over to Heinz. Bear with him just a second as he transitions over to his presentation.
Thank you, Jeff. I will get mine cranked up here and minimize that and go to the beginning of the presentation. Again, good morning, everyone, and welcome to this month's seminar. Again, it's going to be on the Banner SC XS 26-2. Basically, the programming of the two devices is identical. The difference between the SC and the XS, of course, is that the XS has additional I/O. We have done presentations on this product before, so I'm going to do just a very quick overview of the basic programming, and then we will dive into a little bit more of the functionality of the function blocks. As you may remember, the hardware is set up very simply by selecting the base controller and then adding by clicking on the right hand plus here the hardware modules that you want to add. As you then start to populate your terminals, you click on the bottom plus under any one of these, which pulls up the drop-down tile, which has the various icons. In this particular image, I've chosen the emergency stop, and you then select the contact configuration, and with that, it automatically assigns terminals. If you want to override those, of course, you can. We have both the safety inputs, which are shown here, and also the non-safety inputs. In terms of tricks and traps, something to remember is that you want to have at least one manual start input terminal. You do not have to use it in logic, but you want to set it up as the system reset. You will need to do a system reset every time you load or reload the program into your controller. And that's a lot easier than cycling power, which is the other alternative. If we take a look at the functional view, this is where the various I/O or the inputs that we added a little while ago show up again in this reference. This is the functional logic area. I can select from logic blocks the and, ors, not, nands, this sort of thing. The function blocks, which are the more complicated subroutines, which have actually been built and tested by a third party, that they do what they need to do and that the functionality meets the current standards. In addition to that, we have the third variable, which is the reference. This is something that we use when you have multiple pages, so you can look at a variable or connect a variable which perhaps you loaded onto the first page and use it on subsequent pages. Here is a little more detailed view of the programming. Remember, in the upper left, we have the information as to what functions still need to be accomplished in order to have a valid program. You can see here it says, gee, I've got the power enable logic block as well as the output not connected. One thing that I should have mentioned earlier, you can see it here under the various items. You want to make sure that you give each of your variables, inputs, logic, output, some functional name that makes sense to you. This will become very important as you have multiple pages or as you later on debug and manage the program. And of course, you've got your skilled trades that can use that description to understand what your function does. I've also shown a situation, there are some rules with regard to what may and may not be interconnected. I've made or attempted to make an illegal connection here, tying the e-stop in as a bypass. We all know that it is against standards to bypass e-stops and emergency stops. So this comes up with a code. If you don't recognize immediately what you're doing and what you have done, you can click on the question mark, and that pulls up the manual. And in the index mode, you can get to the functional view, click on error codes, and that will pull up the manual, actually, which is hiding in the background of your program. And you can look up B6, which is the error we have. And again, it says you may not use bypass mode on an e-stop. To give you a little different viewpoint, the next slide here is actually of 3 pages of logic of a program that I wrote for my simulator. We'll be playing with that a little bit down the road. And this shows 3 separate pages. The first page being what I call the machine logic. This is how the machine is set up. This is a page of light indicator coding, output coding. And this is a routine which we'll talk about later, which actually generates the flasher code. The idea here is both because of the way the outputs are located on separate sheets, as well as keeping some of the logic for the indicator lights out of the machine logic. It makes debugging and maintaining your equipment much simpler. The next picture here is of the wiring diagram. Again, it tells you the terminals that you're hooked to, the type of device you're using, and again, your user tag, emergency stop, system reset, safety light curtain, etc. Okay. This is a ladder diagram which is generated during the time that we're doing the programming, and it again simulates what the logic that you have built with using the Boolean functions, what it would look like in a ladder diagram. Here again, we see the value of the various function blocks and logic blocks having their own name, so that CR02 has a functional name which is the same as that latch in the functional view. This last one is what we call the configuration. This is something that you will ultimately, before you can download the program for the first time or after you make any changes, you have to go through and validate, verify, confirm, whichever term you're comfortable with, the fact that the program is set up the way you want it to. This gives you a list of all of the variables and their configuration, whether you pick them or whether they're default. And I sort of put this conglomerate together. You can see up here, here's some of the inputs: the emergency stop, manual reset, optical scanner. That's the safety light curtain. It's located on M0. These are the terminal. Simultaneity requirement. One thing I'll point out, which I did as an example, don't do this in the real world, is we have slowdown or anti-bounce delays, both the transition 1 to 0 and 0 to 1. To make a point and show you how this is documented, I added 100 milliseconds over the normal default 6 millisecond close to open. This is not something you would typically do, certainly not in a safety light curtain. In a practical application, I did it here as an example. So don't follow that one, but we'll just see how it works. Here we've got the function blocks, the type of block it is, the nodes that are available to it, what they're hooked to, and again, the user tag. Here are the safety outputs. Again, same kind of information, how it's set up, physically where it's located, which terminal, etc., etc. We have here the indication that my total scan time of my program is 5 milliseconds. That's obviously a function of the size of the logic I'm using. And here's something which is very important. Notice here, these are the safety outputs. Notice that I have a response time that from the 1 to 0 or shutdown response time. Notice the auxiliary stop and the emergency stop are 21 milliseconds, which is a 6 millisecond delay plus some overhead plus the scan time. Notice the 100 milliseconds that I added up here to the optical scanner, the safety light curtain. Notice that I show a response time of 121, which is 100 milliseconds greater than what it is for e-stop. Again, don't do that in the real world. It was an indication to show that we do keep track for you what the response time is, and particularly in safety light curtain, of course, for your separation distance. You will also notice a couple of these that have NA on them. This is because in my flasher circuit, I use a transition of an input 0 to 1 rather than 1 to 0 to turn off that output. And this is a warning from the Banner folks that says, hey, we typically do not in safety circuits design with a signal 1 or a positive power input as a stop signal. So this is just a warning that says we really don't know whether that's what you want to be doing, and is an alert. Also show me that in a couple cases I have used single input wires. Again, these are the terminals that I used for my flasher. Down here, these are the non-safety outputs. You may remember that there are a number of terminals called I/O terminals, which can be used in 3 different modes, either as ordinary inputs, as pulsed outputs for dry contacts if you need a category 4 PLE where you need to look for wire-to-wire short, or you can map them as non-safety outputs as monitors. Okay, so what we're going to do for the rest of the discussion here is we're going to look at the functionality of some of these function blocks, and we will run the simulator and show how these actually function. I'm not going to use them in any real application because that's so product specific or application specific. What I wanted to do today was give you all an idea of how these function blocks actually operated. One thing that we do have in the simulation mode is that we have the ability to slow down time or even single step time. This allows us to look at short duration intervals that are programmed without having to manually change the timer so we can watch it in a simulation. One word of caution in the simulation, and I'll try to remember to do that again as we get into it, is that remember that if you made an error in the assumption in your design, you're quite likely to make the similar error in your simulation. So remember that while simulation is a very handy tool and can look for logic errors, the final validation of your design must be done in real time. I strongly urge you to write a validation program which includes the safe way to test your system, as well as a document that says these are the results that I expect. Okay, so quickly, a couple shots of what what the terminal equipment section looks like. This is a shot of the simulator. It tells me which inputs are on, which inputs are off. This is a logic function. Again, this happens to be the flasher driver that I just pulled out of the simulator. Again, I set up the program that says I have a flasher request, and the flasher terminal right now is off, and that causes the flasher output to be on. This is a very handy document. It very quickly tells you what variables are on, green, off, red, in standby, inactive, not being used at the moment, and how they affect that particular output. As you can see here, which outputs, for example, are driven through the emergency stops, which are affected by the flasher terminals. One thing that we cannot do in the simulation, but which is a very handy bit of software support that Banner's provided us in the live mode when we go live, is that if there is a fault on an input, for example, it tells you that there's a fault. It tells you who it is. In this particular case, it's the emergency stop whose user tag is emerge stop. Not overly unique, but at least descriptive. It tells you which output it affects. Furthermore, if you look down here, you get not only, again, the error code, it tells you it's on module 0, the controller, the user tag, and an error code. You again go to the question mark in the tool, go to the troubleshooting guide as you go through here, open that up to the fault code table, and you get a list of fault codes. I have opened this up to fault code error 2.2. It says it was a simultaneity fault. One of the contacts didn't cycle in with respect to the other. I need to fix that, get them to cycle together. And while I've cut a little bit of that off, I apologize. It tells you what some of the remedial things that I can do to try to fix the problem, check the wiring, check the input, so on and so forth. These are shots very similar to the ones we looked at in simulation during this fault event. See that it shows me in the equipment mode, it shows me in the wiring diagram. Notice here, this was an E-stop. I have two normally closed contacts, yet one is high and one is low. That tells me exactly where my problem is. I can go out and fix it with no further ado. And again, here again, in the functional view, it says as long as you have an E-stop, obviously, an error, we're obviously not going to work. Okay, so much for that. What we'll do now is we'll start looking at some of the various function blocks. The first one that I'm going to use as much of an example as anything else is the solid state output. I have the ability to select certain functionality of that output block, such as an external device monitoring input, which I strongly suggest in any dual channels, the ability to monitor the response time, set it up as a latch by itself, and set it up as a separate reset. I also have the ability to split the outputs from a dual channel to a single channel. This is the transistor version only. Each one of those channels will still have a dual transistor redundancy, so that if you split those, you may still use that single channel output as a category 3 PLD, as long as you can exclude wire short to another power supply. Also, anytime that you have any thoughts or questions, this is, gee, what does this part do? You click on the info and that pulls up that section of the manual already indexed for you. I can also, depending on the tile, if I have both advanced and basic functions, these happen to be the basic. This is a toggle, and here are some of the advanced functions. This is where set up, on, off delay, etc. Okay, so let's start with the first one, not necessarily in any particular functional order. I think I did it as they are listed in the drop-down manual. So let's talk a little bit about muting. Muting, of course, is the function to be able to, under your control, through some external devices, to suspend looking at the output of a safeguarding device for a specific period of time. In this particular case, the unit is capable of accepting either one dual channel input or two dual channel inputs for sensors. In this particular case, I chose the X, which means I have only one sensor pair. What we'll do now is we'll go out of the PowerPoint presentation and, whoop, I better kill this. I'm sorry, wait a minute. Get rid of this guy, and I should be able to now download the example program. So let's do that. Sorry about the delay here. And this is the muting diagram. And what we'll do now is we'll go over here and we'll go to the simulation mode. I am now in simulation. A word of warning, always make sure you start the timer before you start making changes in the input. If you fail to do that, you will get some odd responses when there's leading edge transition. If you run into that, the best thing to do is get out of simulation, pop back in, and that resets things. So we'll start the timer. Notice here that I've got the safety light curtain. When it's on, the output it goes on. Not real startling there. I have the ability to manually or through another input enable muting capability. I will go ahead and do that. I will trip my two sensors that says I'm in the muting mode. My module goes to purple. You can see the clock here running. And if the safety light curtain is now blocked, I continue to have an output. If it comes back on, either way. Okay. I could, if I wanted to, now lose the enable because that's only a leading edge. The value of that variable is that I can limit when muting takes place. For example, if I've got a material going in on a conveyor, I may want to mute only when the conveyor is running in the forward mode, and maybe make it a little bit more difficult for somebody to defeat it. I also have the option of being able to override the system. Let's assume that I've got a conveyor system on a body in white. The conveyor stops, and now I've got to get it started, but my muting has run out. I can manually go to a separate function and force that output on. There are a couple of options which I didn't detail, but you can do some logic here that says under these circumstances, I want to override that muting function. Okay, let's see whether we can get our PowerPoint back. And we'll go to the next example, which is bypass. It's probably one of the simplest variables. We have only two inputs, an in and an out. There is one option which is available in the configuration. You see this right here. It says you have the option that when both the bypass and the safety function are both true, the output will go off. You can either enable or disable that. Okay, we'll stop the former simulation, open the next project, and here's my bypass. And again, this one will be a little bit anticlimactic, but it will show you a feature that we're going to use in one of the tricks sections. Here again, the input is high, normal. Okay, it goes off. I go to my manual override. Again, here's my timer. I check the both off, drive off, and you can see that the output turned off. Okay, nothing, like I said, nothing real earth-shattering here, but it does give you the ability to manually bypass. Remember, it is up to your safety circuit and the operator to decide when bypass is appropriate. Notice that after the timer times out, obviously the output goes on. In order to reset the timer, you have to recycle the bypass mode. Okay, one of the things that is true within the XS and CS system is we do not have a separate timer block. That's something that's coming down the road, but at this point we don't have it. So we've got a workaround. Basically, what we're going to use is use the timing function of the muting function and set it up as either an on delay, an off delay, or a pulse timer based on the logic we use. These functions are just plain bypass. Each bypass must have an input, so I've got a dummy here which should never be connected, because if I connect that dummy to a hot wire, all of the outputs will go high, which is really not what we want in a timer. So let's take a look at how this rascal works. Again, we go to open a project and go to, and let's see, on-off pulse. And what I did here is I wrote those three programs. Again, we'll go to simulation, and what we'll do is we'll look at the pulse timer, the on delay, and then I'll turn the input back off and the off delay will come on. Here we go. There's our pulse, there's our on delay, and if the time event, whatever that is, and that, by the way, can be real hardware input or a logic function. When it goes back off after X amount of time, that goes on. One thing that I did add here, notice that if the dummy goes high, all of the outputs are driven off. That's just in case somebody accidentally drops a wire on that, so that all of your timer functions don't show up incorrectly as timed out. The time duration that I can set on the bypass is from 1 second to 12 hours. There are times when we need a timing function which is a skosh bit less than 1 second. And we have an option for that as well. You may remember in the previous we indicated that we do have off delay capability. And here we are at we're going to use a safety output and its on-off time delay as our timer function. Here, obviously, I would split the outputs so that I don't use as many variables, use them for something else. I do not need to connect the output to anything. I do not need to hook it back to an input. I can use, remember we talked about references. I can look at the reference value on these outputs. In this particular case, the on delay and the off delay. So look at the reference values and put that into some kind of a logic block that says, yes, the timer event is taking place, and this is the status of the time delay variable output. We'll get you a shot of that. This is under the, whoop, wrong one, there we go, short duration. And again, this is going to be somewhat anticlimactic, but just to show, yeah, indeedy, it does work. Here's the on event, and there's the off event. If that was very short, I could go back here, stop the simulation, go to 10% speed, turn it back on, and lo and behold, even I can react to the timing there. I can also single step it. I don't use the single step too often, but if I remember correctly, if I do this in this many cycles, where am I here? Let's turn this guy on so we can see it. It should clock down in 20 milliseconds, and I'm not getting that. I apologize. I thought I had that figured out. Well, sorry about that. We'll move on. I'll have to take a second look at that, what it is that I am doing wrong. Maybe I have to be in 100%. Well, sorry about that, folks. The beauty of live demos. Let me go on to the next topic then, and that is the flasher circuit. I had an application where there was a need to have lights flashing. The customer wanted different flash rates and so on and so forth. And what I did there is I used the on and off delay of the anti-bounce of a real input and set up a period. I set up basically a multi-vibrator. The input goes on, it turns the output off, and vice versa. With those two delays, I can control the on and off time of a driver to a flasher light. And we'll take a look at that next. And that is the application flasher. Now we'll take the final version. You may recognize this from the first program that I showed you in the 3 sheets. This again is the machine function. We'll go into simulation, get the simulator running, and we'll set on the 2 emergency stops are both released and reset, but the program requires the operator to reset that function at the logic level. hasn't been done. That gives me a eStop flasher request. I go to the next sheet and I said, well, that's not doing anything right now. Let's go to the third, and you see that my request with an indirect reference says, yes, there is a request. And what we'll do now is we'll enable the light drivers. Whoops, wrong one. This allows this thing to flash because every once in a while I've got this running on my desk. I like to be able to turn those off. And as this output now came on the flasher input, my off to on delay turns on. I now have a flasher drive to my light, and my flasher terminal driver that goes to the terminal goes back off. And here we've got a flasher. If I go back to, I'll leave it in the on mode. We go back to the light drivers. You see here, here's that same and that was flashing with the terminal. Obviously, by changing what is valid, I can turn the safety light curtain on and not do a reset. And now I have a request. Well, let's go ahead and clear this out so we got not too much to look at. I now have a flasher request for the slow terminals. And basically all I did was change the duration of the on and the off delay. You can even get them both to run and get some rather interesting patterns. We'll take a look at that in live if we have time. Going back now to the next function block. This is going to be the two-hand anti-tie down. This is a very useful function. I have a lot of selections I can make for it. We'll talk you through a couple of them. First of all, I can have up to 4 sets of two-hand anti-tie down, each one having to work correctly. If any one of those 4 that I've modeled go low, then all 4 of them the other 3 have to cycle as well. In this particular example, I have only 2 of them, TC1 and TC2. I also have the opportunity to mute 1 or more of those, say on the upstroke. I want to mute one of them. I can set that up again here by saying I want to mute, and this is the one that I want the mute to function on. This obviously is a little bit bad. I've only got that for 30 seconds, but whatever the machine requires. So let's take a look at the functionality there. And this will be two-hand anti-tie down. Go to simulation, and you see this got a little bit busier. I've added a second one because I want to show you something else. So we'll take a look at these one at a time. Let's just, first of all, I've got an emergency off override so that if this line goes low, the two-hand anti-tie down function drives their outputs off. Here are my two-hand anti-tie downs. The outputs go on. I lose one, they go off. I turn it back on. I still don't get the output here. As you know, I have to remove both of those in order to get them back on. Okay, let's go one step further. The machine is running. It is running forward. Say this is a crank. You want to be very careful that if you do muting based on cams, you have the direction of the cam, of the crank included, because otherwise when it's running backwards, your muting would be at the wrong time, would be when the RAM is coming down rather than when the RAM is up, which is obviously what you want. So we'll enable that. We turn the mute on. We see the mute is running. The device that I muted was TC2, if I remember correctly. I let go of that one. Notice where both of them are just tied in here. This dropped. I continue to do my muting. The machine continues to run until, in this particular case, the timer times out, which is just about now. And now it turns off. And in order to get another cycle, both the muting command and both of the push buttons have to be released. And here we are again. And so it goes. Okay, there is another possibility that there might be, and that is this bottom unit. This one I have set up without the muting, but I have put a bypass block as the two-hand anti-tie down as one of the inputs. Notice again, I've got the one here directly, but this one goes through a bypass block. So if both of these are on, the output goes on just like it's supposed to. But let's assume I've run a project where I only want to run with one operator, and I put an interlock gate over the access point of the operator for the two-hand anti-tie down that I no longer want to use right now. If I fire that rascal up, notice I go into bypass, and I can set that up for up to 12 hours, so I can certainly run it on a per shift basis. And now this operates as a one operator two-hand anti-tie down. All the function of the two-hand anti-tie down still apply as long as the gate is closed. If the gate is opened, then of course I have no output unless I operate both hands. And as I indicated before, and this is not selectable in this case, if I have both the two-hand anti-tie down and the gate high, it forces that bypass off, because obviously there's something not right here if I think I'm trying to control it with the two-hand anti-tie down and the gate is closed. Okay. We've talked about that was the bypass one. The next one we want to talk about is the enabling device. This is something that is a very, very handy device. This is particularly useful for setup and so on, where we need to run some function behind an interface guard, and we want to be able to jog or otherwise move some function under power, but we want to make sure that the operator has good control over it. So these are the bypass blocks. I can set them up with different features, and I'll show you each one of these three. Again, I have an off override, and the other thing to remember is that every time I leave the enabling device mode, I must reset to revert back to the safety function. Okay, enabling device, and we'll get the simulation going on that guy. Run the clock, and again, first thing to do is turn on the e-stop so that the unit will run. We'll do the simple one here, and we'll energize, hold in the enabling device. Remember, this has to be a special device that operates now per the standard, both when you hold it, only when you hold it in the middle. If you let go or over travel it, it shuts down. So that's a change in the standard. It used to be just when you over traveled it, and they found, rightfully enough, that some people, when they are in a panic situation, squeeze rather than let go. So this has been a change in the standard. So as you can see here, I can jog for X amount of time, putting power on the unit. However, I really don't want to run the hazard off of the enabling device. So I've got another version here which allowed me to add a jog input, which now, as long as I'm, timer ran out. Let's do this. Let's slow that guy down a skosh bit. Talking too slow here, I guess. Okay, we'll cycle it now, and now I can now cycle the jog. The output will come on when I'm enabled and I am jogging. If I let go of the enabled device, obviously they turn off. There's one other feature. Turn all of these guys off again, and that is this unit here where I have a separate jog output. In this particular case, when I go to the enabling mode, I have the ability to turn on some power, but I have a secondary output which cycles only with the jog button. This might be something that you would use in a variable speed drive where you want to enable the drive with the jog power, but you've got a slow, safe speed jog. This is a technique we use quite a bit to reduce the hazard by slowing the motion of the hardware down. It increases your possibility of escaping. We'll assume that we're done with this now and we want to go back to normal mode. If we just now have the gate closed, nothing will happen. And the reason is we have not done a reset, which says, yes, we are indeed ready to go to that. And now if everything works right, our 3 outputs go high. The jog buttons, while I can turn them on and off, obviously do not perform any further function. Whoop, one too fast, one too far, bridge too far. Okay, the next one is a rather handy unit. It's called a reset block. You and I typically call them memories. In the transistor world, they're called flip-flops. What we do with them is we have the ability to monitor some inputs, and when all of those inputs are true, we can acknowledge that and then set up the function that said some other function, such as the reset cycle, occurred, and we remember that until we lose one or the other, in this case on a 2-input and one or the other of the inputs. And let's take a quick look at that. Remember to download it. Let's see, reset block. Again, this is not earth-shattering, but sort of confirms. It's nice to have a good feel for how these guys work. Again, in this particular case, I have a 2-input AND. When both of those ANDs are true, I can enable the output. Okay? And this is, by the way, I must use a reset button from the non-safety inputs. It's one of the requirements of the program. So I've got this one set up in what they call the monitoring mode, and you can see it's working this way. It pulses. I push the button in. The reset doesn't occur until after I let go. This reduces the probability of somebody trying to build an automatic reset with the toothpick from lunch. There is, however, the possibility that there are some special conditions that I have when I want to restart. So what I did with that one of the options that's available in my drop-down tile is I can add a reset enable. Notice here that while this one went on with the 2 inputs high, even though I feed the same thing to the input, this one did not. And that is because I do not have the reset enable true. Let's say that you don't want to start the machine unless the hopper is full or something has returned. You have some known variable that needs to be in a given position in order to restart the machine. So you wire that into either hardwire or through logic in the reset enable. And now when the input goes true and I push the reset button, happen to use the same reset button twice, this turns on. I can lose that and still continue to stay on because all this guy does is enable the latching function to occur. It does not reset the latching function as the in variable does. The last unit we want to talk about in terms of function blocks is the flip-flop. And the flip-flop has one functional advantage. I can use logic levels for both my set and reset, whereas in the reset block, I have to use that push button, which generally works, but there might be something in my logic that I just want to remember that that activity took place. There are 2 types of flip-flops in the program, an SR and an RS. Very important that you understand the difference between the two. It's simple, but can be problematic if used incorrectly. And we'll pull those guys up so we can see the functionality here. Flip-flop. There we go. Go to simulation. And we have here the fact that with both of the set and the reset off, the output is off, rather nice. We do a set. Whoop. Remember I told you got to start the clock? There I am. I forgot to start the clock. Okay. I've got my set on. Both my set and my reset turn on. I let go. They stay on. I push the reset and they turn off. The thing that's different between the SR and the RS is that the SR is set override and the RS is reset override. So that if both inputs are high, the SR turns on, the RS turns off. This is quite important, even though typically in a good design you won't have both set and reset high at the same time. You want to decide, should that happen, what do I want my output to be? In most cases, in the safety function, if this leads directly to shutting off a safety function, you do not want to use an SR. You want to have it off override. Unless, of course, you're designing some pumps on submarines, in which case the on may be the safer of the two modes. The last thing I want to do is I have here sitting next to me, I know you can't see it, but I have a running simulator which is running that Flash program, and I just want to show you a couple of the functions that we simulated on the simulator and see whether we can get them running actually. What I'm going to do now is I am online. I'm going to try to upload the program that's running on the controller into the simulator program or into the configuration program. Do the import configuration. I input the magic password. And here I am with that program. You recognize this one already. I go to live. And now you gentlemen are watching my program, which is a series of lights and toggle switches. Let's take a quick look at the program, and you'll see something right away. Notice here I've got two sets of flashing lights. I've got both the e-stop and the safety light curtain to be reset. You can see here how the flashing circuit works. What I'm going to do is I'm going to reset one of them so you can see it a little bit easier. I just reset the emergency stop, flasher request, and now I have just the safety light curtain. Again, all I'm doing is turning a terminal on and off, which I call slow flash. I have two long on and on delays on the other one. That's another terminal. I just have a shorter time on each. I can run them both together, which really looks interesting because then I have multiple flashes because both of these try to drive it on and off based on their time period, and I get sort of a stroboscopic effect. Obviously, the better solution is to set up the code so that if I have multiple requests, only one of them at a time is decoded to the flasher. You may remember that we had this particular layout before in the simulation. Again, this is the status of the variables and what's going on. What I'm going to do is I'm going to go ahead and reset everybody. And now my machine is running. Notice here the EDM, external device monitoring, changed from the green, which said the normally closed contacts were closed, to the normally open, and that's how it should be. The last thing I want to demonstrate before we go to questions, if there are any, I think I'm getting close to my time, end of air time, is I'm going to generate a fault, and I'll let you take a look and see if you can figure out what it is. And notice here, again, just like we had in the simulation, I've got an emergency stop fault. It's on M0. It's that variable. It is error code 2.1. Let's take a look at what else this program tells me. Number one, again, here's my hardware equipment. It says, yep, I've got a problem on the emergency stop. I take a look at the wiring diagram, And here it is again. And in this particular case, again, I've got that problem. I go out there and I say, well, okay, fine. What do I need to do? I've got it fixed. In order to clear the fault, I cycle them both correctly and the fault is gone. One other thing to show you, again, I generated the fault on purpose. Nice when you can do that rather than have the machine do it for you, is to go to the functional view. And if we go back here, it even, let's see, where am I? I should have just created a fault, but I didn't. There we go. I forgot to turn it back on. Even when I hover over this particular error, it again shows me that it's error 2.2 and an emergency stop. The reason it didn't show up before is I had a dynamic failure. I just pushed one of the two buttons that simulates that unit, that e-stop, and released it, and that caused the error to go away. I had to put in a hard failure. That is the extent of my formal presentation. We have a couple minutes left, I believe. Jeff, do we have any questions?
Heinz, I don't see any in my panel. Go ahead and open yours up there and see if we see any right here. Yep. And open up that questions box there. I do not see any questions.
Well, either we've done a good job or you've all gone asleep or left. In any case, I certainly appreciate you attending. And this time next month, we will have another webinar. I think it's on conduit and wiring, if I remember correctly. Again, thank you very much for attending. And again, this is Heinz Knackstedt for C&E Sales. Have a good weekend coming up.